Uh, Now in the previous sessions we just finished all the plots of the frequency response, Bode plot, polar plot, Nyquist plot. Okay. Now we continue the subject now with the topic of one important topic for the GATE examination point of view. Now this is controllers and compensators. Okay. So have you heard anywhere in the control system subject so far the word controller? Yes. Now we start our subject with a block diagram of a control system. Now in that we just see the first part of that particular block is a controller. Am I right? So what is the purpose of this controller? Now a controller is a device which is used to produce the desired performance of the system. Okay. A controller is a device which is used in the system to get the desired performance, to get the desired results. So you tell me what type of systems generally what we are using. So what is the features your system should have? What type of features is required for designing of a system? Now obviously for a control system, the best control system is nothing but first point in our mind without any second thought. It should be a stable system. It should be a stable system. Now this should be the first feature what we require for designing a best control system. Now what is the second feature? Now this best system is to produce minimum error, or of course minimum steady state error. Minimum error or minimum steady state error. Is it right or not? So these are the two features such that now that system should be the best system, we call it. Am I right or not? So now you tell me, now this is a stable system. So how we can identify this particular stability? If you want to identify this particular stability, we required closed loop poles. Now of course these closed loop poles are available in characteristic equation, or this characteristic equation is a part of a closed loop control system. Is it right or not? So this stability is decided from closed loop poles. But once if you have a closed loop poles, so you are in a position to decide the stability, time constant, frequency, characteristics and everything or not. So which is nothing but, now with this we can easily find the transient state analysis. The transient state analysis or the transient state behavior. So if you want a best transient state response or a best transient response or a best transient state performance, so we require the closed loop poles. So that closed loop poles are available in the closed loop control system, or directly you can get it from the characteristic equation. So for doing the system stability or transient state analysis, you concentrated on closed loop poles or a closed loop poles which is available in the characteristic equation. But this is not only itself will give the best system characteristics. The best system characteristics means stabilize the system and to produce minimum error or minimum final error. The steady state error means you know that the steady state error is called as a final error. Is it right or not? So you know that the steady state error depends upon type of the control system. The steady state error depends upon type of the control system. The steady state error depends upon type of the control system, where type is always identified from where you can get the type. Type is the parameter which is obtained from open loop transformation. Type is nothing but number of open loop poles at origin. Number of open loop poles at origin is called as type. Is it right or not? So the type, the steady state error depends upon the type. Type is nothing but it is a number of open loop poles at origin. Open loop poles means now we required a open loop control system. We required a open loop control system transfer function g of s. So we want a best system means a minimum error or a minimum steady state error. Now this part is nothing but steady state analysis. This deals with steady state analysis. So the best control system or best closed loop control system or a best system is nothing but I want a best transient state analysis and I want a best steady state analysis. Understand or not? So in order to produce this particular features, so for actual systems which we want to use now let us take this is an actual system. Actual system. Now for this actual system we need to apply some controller. We need to apply some controller. So when we want to apply this controller to this actual system, now this controller is producing some controlling actions on this actual system such that now that actual system will try to get the best performance or a best characteristics is nothing but a best transient state analysis or a best steady state analysis. Understand or not? So what is the features of this controller? Now this controller is a device to get the desired performance of the system. So in order to get the desired characteristics, so which we want to use this controller to the actual system. Okay. So this is actual system, but that actual system is to produce the minimum error or a good stability, right? Or a less error or a very good stability. So you require this controller to the actual systems and you can get the desired characteristics or a desired performance. Okay. So the best system is nothing but we required smallest rise time, smallest settling time, and minimum error or minimum steady state error. Now these are the best characteristics of a system. So we required this one to get the we require this characteristics. So use the controller to the actual system. Okay, no doubt. Okay, so this controller is a device to get the desired performance of the system. The desired performance of the system is nothing but it control the transient state analysis or it will control the steady state analysis. You write that point also. Desired performance of the system means control the transient and steady state behavior. And so if you use this controller to get the best transient and steady state behavior, then you can get smallest rise time, smallest settling time, comma, minimum error and less peak overshoot. This characteristics you can achieve when we are using the controller. So to get this particular characteristics or to control the transient state or steady state, then we use the controllers. Okay, this is the uses of controller. Okay, no doubt. Now this is a clear idea about the controller. Okay, so now which controller will improve this response, which controller will improve that response, that we will see one by one. Okay, first you note on this. Okay, so this is the main. If you understand this particular point, then you can easily understand the behavior of the controller. Okay, now see here. Now I just give first controller. This is the controller. Now the controller will produce controlling actions. The controller will produce the controlling actions for the input. What is the input to the controller? The input to the controller is an error signal, you know that. Now this is the input to the controller, is nothing but an error signal. This is the controller output, is the controlling action. Now this is the controller input, is nothing but the error signal. So this is input, this is output. Now this controller is in the forward path, right? This is the controller is in the forward path. Now see here, let us assume this is the input E of t, controller input which is represented by U of t. This is the controller output, is nothing but controlling actions, I am represented by P of t. And this is the controller which is in the forward path. Therefore, I just take this is the forward path gain G of t, but this is the gain of the controller. Therefore, I just mentioned GC. This is the controller gain which is in the forward path. Okay. So now see here, controller output, controller input, controller gain. I just find the controller transfer function first of all. Okay. Now if you want to find the transfer function, apply Laplace transformation. Now what is the Laplace transformation of GC of t? G of s. Laplace transformation of output P of t is P of s. Laplace transformation of input E of t is E of s. So what is the controller transfer function? Now the controller transfer function is controller transfer function. Laplace transformation of output P of S by Laplace transformation of input E of S, which is equal to GC of S. Now this is the controller transfer function. This is the controller transfer function. Laplace transformation of output to the Laplace transformation of input is nothing but the controller transfer function GC of S. Clear or not? Now this is the controller. Now this controller will generate some controlling actions based on the input. So any controller whose controlling actions is completely depends upon error signal. Okay. Any controller whose controlling actions completely depends on input. Input is nothing but the error signal. Any controller, whatever may be a controller which we are using. Okay. So finally what you can understand. So based on the error signal, controller will produce some controlling actions. Understand not? Based on error signal, controller will produce some controlling actions. This controlling actions is operated on actual system. I am mentioning earlier, actual system. So when this error signal, based on the error signal, controller will generate the controlling actions, and that controlling actions is working on the actual system. Sir, what is that actual system? So practically what is the controller diagram? Okay, then that we will see. Now first you just note down this. Okay, so this is the controller transfer function. The controller transfer function is nothing but the controller gain itself. Okay, and any controller is completely depends upon the error signal. Now I'll write the controller exact block diagram. You just see here. Now this is the comparator. Comparator will give the difference. Therefore that difference is nothing but error signal. Now this is the controller. Now this controller will produce some controlling actions. This controller will produce some controlling actions, and this controlling action is going and operated on the actual system. Now listen carefully. Based on the error signal, the controller will generate some controlling actions. This is the controller. This is the controller will produce some controlling actions. That controlling actions is going and operated on the actual systems. Some of you are saying actual systems. Now this different names. This is the actual system. Previously what I am saying is the controller will control the transient and steady state behavior. So now that will apply to the actual system. So this is actual systems, or practically this is called as a plant. Earlier crosses you are also called as a processor. But this is the exact name, actual system plant. No sir, actual systems plant we don't understand sir. Now you tell me sir, what is exactly it is. Now students listen, this actual system, now this plant is nothing but practically this plant is nothing but it is an open loop control system transfer function G of S. Understand or not? So this is the this is the plant. Now this plant is nothing but a open loop control system transfer function G of S. So what you can understand students, what is your understanding? So based on error signal, controller will produce the controlling action. This controlling action is going and operated on this particular plant such that this plant performance is improved. Once the plant performance is improved, then after improving this plant performance, then you just connect it to the feedback and it will be converted to the closed loop control system. Understand or not? And once again I repeat, based on the error signal, the controller will produce the controlling action and that controlling action is going and operated on a plant. The plant is nothing but practically it is a open loop transfer function such that this open loop transfer function plant performance is improved. After improving this plant performance, you just connect it to a feedback, then it will become the closed loop control system transfer function. Understand or not? Now then it will become the closed loop control system transfer function. After improving the plant performance, you just connected, this is C of S you just connected to this particular plant now such that this plant performance is improved. Okay, this is the actual closed loop control system. So now students, then I just want to explain now each and every individual controller, right? Now first I want to say without controller. Without controller means this is the only plant. This is the only plant. Okay, or a plant is nothing but only open loop transfer function. This is the plant or this is the actual system or this is the open loop transfer function. Okay, so just take down this block diagram, then I just give without controller, with controller, what happen we will see. Okay, note down. Okay, now students, you just observe carefully. Now without this controller, okay, without this controller means remove this controller only. So if there is no controller means only the actual system or only a plant or only a practically it is a open loop transfer function. Now without controller, what is the block diagram? Now see here. Now this is without controller. Without controller, which means only plant. Okay, without controller, only the plant is nothing but only the plant, no controller. Let us take this is the plant 1 by S into S plus 10 is practically a pure open loop control system transfer function. Now students, you just observe this is without controller, means there is no controller, only the plant is there. Only the plant is nothing but pure open loop control system transfer function. Let us assume this is the open loop control system transfer function G of S, now which is nothing but 1 divided by S into S plus 10. This is the open loop control system transfer function and the number of open loop poles available at origin is 1. Therefore, this is nothing but type equal to 1. Because you know that the type and steady state error is interlinked. When type is more, steady state error is less. right? But here when type is somewhat less, therefore I may expected that the steady state error is somewhat more. Let us assume, for example, this is somewhat more, okay, right? For a comparison purpose, I just give this 100, okay? Don't confuse where the 100 is coming. This is somewhat more value. Then after connecting to this controller, then that error will be decreased or increased, we will see, okay? Now this is the error part, okay? This is the error role. This error role is nothing but what? This is talking about the error value. The error value is nothing but the error is nothing but a steady state analysis part. This is the steady state analysis behavior. So error and calculations of error and steady state error deals with steady state analysis part. Okay. Then what is the transient state analysis? So if you want to find the transient state analysis, we require closed loop poles. The closed loop poles are available directly in the form of characteristic equation. So what is the characteristic equation? The characteristic equation, which is nothing but 1 plus g of s is equal to 0. So 1 plus g of s equals 0. Therefore, s square plus 10s plus 1 equal to 0. This is the characteristic equation of order 2. And s square plus 2 zeta omega n into s plus omega n square equal to 0. Now this is the characteristic equation of order 2. Therefore, omega n, which is nothing but 1 radians per second, 2 zeta omega n, which is equal to 10. Students, you just see here, 2 zeta omega n equal to 10. Therefore, zeta, which is equal to 5. When zeta is 5, which means that zeta is greater than 1. Now students, if you just observe, when zeta is greater than 1, where are the poles location? Zeta greater than 1 means the poles are on the negative real axis at different location. System is 100% stable system. But what is the response? The actual response or the transient response, which is nothing but if the poles which is on the negative real axis, the response is exponentially decaying. But this is delta greater than 1 means this is which response? Over damped response. Is it right or not? Now students, this is the over damped response. Of course a stable system, and of course somewhat error should be more. Then this is the without controller. Is it right or not? Now this is without controller. Now students, now I am talking about with P controller. What is the controller I am taking? With P controller, what happened? First of all, we want to see what is P controller. Okay, what is P controller? Now see here, what is P controller? Now, first of all, we want to see the controller. Now, this is a P controller. Now, this is called as P controller is nothing but proportional controller. Which controller? Proportional controller. Now, what is a proportional controller? The proportional controller is nothing but controlling actions. So why this is called as a proportional controller, or whatever may be a controller, any controller whose input is error signal, controlling actions depends upon error signal. So this is P controller. Controlling actions are directly proportional to error signal. Controlling actions are directly proportional to error signal. Therefore, this is called as proportional controller. The controlling actions are directly proportional to error signal, which means error is not present. When error is present, controller is on position because controlling actions are completely depends upon the error signal. When error is not present, controller controller is off position. When error is present, controller is on position. When error is not present, controller is off position. Therefore, this P controller, the proportional controller, is also called as on-off controller. This proportional controller is also called as on-off controller. The P controller is also named as on-off controller. Understand now? The proportional controller is also named as on-off controller. Now students, you see here, now the controlling actions are directly proportional to error signal. Now the controlling actions are directly proportional to error signal. So controlling actions are represented by P of t is proportional to error signal is represented by E of t. Then if I apply Laplace transformation, what happens? If I apply Laplace transformation of P of t is P of s, Laplace transformation of E of t is E of s. If I remove this proportionality, we'll put a constant. Now this is the constant k or a gain. Now this is the k in which controller? This is which controller? P controller. Therefore, this k is represented as kp. What is kp? A kp is nothing but proportional controller gain, or proportional controller constant. Now this kp is nothing but proportional controller gain or proportional controller constant. Therefore, now finally see here, what is the P controller transfer function? The P controller transfer function is the proportional controller transfer function is Laplace transformation of output by Laplace transformation of input is nothing but the controller transfer function GC of S, now which is nothing but only Kp, a proportional controller gain or a proportional controller constant. Therefore, now we will see what is actual plant. Now this is the actual plant. What is the plant? The plant is nothing but 1 by S into S plus 10. This is the plant performance without controller, steady state analysis and transient state analysis. Now we will see now this plant, how this plant is affected by using a controller. Which controller? Now how this plant is affected by using a P controller. What is a P controller? The P controller will produce a gain of Kp. Now we will see with P controller, what is the steady state analysis? Now with P controller, what is the transient state analysis? Okay, now first you just note down this, student. Say, understand or not? Now first we will see without controller. Next we will see with controller. Okay, note down. Okay. Now students, this is the P controller transfer function. Now we will see, you can easily understand. Now without controller and with controller, what should be the difference? Okay. Now you can easily understand now. Not a problem. Now students, you just see here. Now without controller, no controller, nothing, only plant, steady state analysis and transient state analysis. System is stable, closed loop control system is stable, but error is somewhat more. Okay, so this is without controller. Now we will see with P controller. Now students, you tell me, this is without. Now what happened with? Okay, now with P controller, with proportional controller, with on off controller. So you tell me, what is the overall forward path gain? The overall forward path gain is nothing but this is the overall forward path gain or not? Because this is S domain, this is also S domain. So what is the overall loop control system transfunction? With P controller, G of S, which is equal to Kp into 1 by S into S plus 10, which is equal to Kp by S into S plus 10. Now is there any change in type? No, type equal to 1, only type, there is no change in type. So what should be the steady state error? Now the steady state error will be same 100. Okay, so which is not gets affected. Then what about the transient state analysis? This is the story about the steady state analysis with P controller. This is the steady state analysis. What is the transient state analysis? Now see here, what is the transient state analysis? Transient state analysis means, now first we want to find the characteristic equation, right? What is the characteristic equation? Now see here, the characteristic equation, which means that 1 plus G of S equal to 0. Therefore, SS square plus 10S plus Kp equal to 0. Now SS square plus 2 zeta omega n into S plus omega n square equal to 0. This is the characteristic equation of order 2. So now students, now this is the characteristic equation of order 2. So now the proportional controller will produce some gain. Okay, the proportional controller will produce some gain of Kp. So the gain, so we can change whatever the gain we require. So now see here, let us assume, for example, what should be the transient state behavior if Kp equal to 25. If Kp equal to 25, what happened? Now you just compare. If Kp equal to 25, omega n square equal to Kp, which is equal to 25, which is equal to therefore omega n, which is equal to 5 radians per second. Now 2 zeta omega n, which is equal to 10. Therefore 2 zeta omega n 5, which is equal to 10. Therefore zeta equal to 10, 10 cancel, which is equal to 1. 2 into 5, 10. Okay, when zeta equal to 1, you can immediately identify. When zeta equal to 1, where are the poles location? Now this is the poles which are repeated poles on the negative real axis. Now this particular transient response is called as a critically damped response. When damping factor zeta equal to 1, this is the critically damped response. You know how the critically damped response, okay? Now this is one ramped behavior and this is one exponential decaying behavior. Now the critically damped response is nothing but a combination of these two. Now this is the critically damped response. Now this is critically damped response. This is the critically damped response. Okay. Now this is the critically damped response. Of course, the system is stable. So this is when Kp equal to 25. Now let us check when Kp equal to 100. When Kp equal to 100, omega n square, which is equal to 100, omega n, which is equal to omega n square, which is equal to Kp, which is equal to 100. Therefore, omega n, which is equal to 10 radians per second, omega n, which is equal to 10 radians per second, to zeta omega n, which is equal to 10. Therefore, 2 zeta 10, which is equal to 10. Therefore, zeta, which is equal to 1 by 2, which is 0.5. Now, when zeta is less than 1, when zeta 0.5, which means that zeta is less than 1, greater than 0. When damping factor zeta is less than 1 and greater than 0. Now, these are the poles location. The poles are complex conjugate. The poles are complex conjugate, and which is left hand side of S-plane. System is stable. Now, these are the complex conjugate poles, which is nothing but the underdamped response. Now, this is the C of TR, exponentially decaying, and a decreased amplitude of oscillations. Now, this is nothing but under damped response. Okay. Now, students, you just observe here. Now, this is without controller. Error is somewhat more, but the system is stable and it produces overdamped response. Is it right or not? But when we are applying the controller with proportional controller, so you just put the Kp gain as 25, then it will produce critically damped response. Then if you take this proportional controller gain Kp as 100, then it will produce underdamped response. Okay, so it will change according to the response. Somebody is required overdamped response, somebody is required critically damped response, somebody requires underdamped response. So now you suggest which controller. Your actual system, in order to produce a different transient responses, then that system is connected by a proportional controller, and you maintain a gain Kp as per your requirement, such that you can get the different types of transient response. Okay, so what is a P controller? The P controller will change the transient response as per the user requirement. Okay, no doubt.